Welcome to all of you. In this session, we are going to understand the verification of the linearity property of DFT using the Scilab. So let us have a first theory about it and then we will enter into the Scilab program of it. Now let us first go through the statement of the linearity property. If DFT of x of n is equal to x of k for all the values of k ranging from 0 to n minus 1, then DFT of a x1 of n plus b x2 of n is equal to a x1 of k plus b x2 of k for all the values of k from 0 to n minus 1. So in this expression, a and b are going to be the constant values and x1 of n, x2 of n are the time domain representation, x1 of k and the x2 of k are the equivalent frequency domain representation. In words, we can say this one as sum of the DFT of individual sequences is equal to DFT of sum of the individual sequences. So this is what we are going to make a proof of. Let us first consider a small example for this one. So calculate the DFT of the sequence x of n is equal to cos pi n divided by 4 plus sin pi n divided by 4 for n is equal to 4 using linearity property. So now this is the given expression and length of the sequence is given. Now we need to apply the DFT property for this. So steps being followed over here. So this for the linearity property what we are going to have. So in order to prove this, first we are going to have DFT of x1 of n and then DFT of x2 of n. So that's what this part we are going to get. X1 of k and x2 of k is what we are going to get. In the second part, we need to get this one. So for that, we are going to obtain first x1 of n plus x2 of n representation. Whatever the value we get, that is x of n. For that, we are going to apply the DFT and that is what the x of k we are going to get. Finally, whatever this LHS part we have got, that values must be equal to the values what we are going to get on RHS part. With respect to the given expression, so the values of a and b which are constants, in this case it is equal to 1 and 1. So a and b we are not going to address separately over here and its value is equal to 1. Now here is the solution for that. So x1 of n, so for 4 values we are going to have these values and for x2 of n for length 4 is what this is what we are going to get. Now calculating individual DFTs, x1 of k for this one we are going to get as this value. If we apply the DFT, x2 of k is what we are going to get, that is over here, this is what we are going to get. Add those two results and this is what the first part of the result we are going to get and this is actually the RHS part of the result. Now LHS part. So time domain values, first add them together. Add them together. That means these values are added together with respect to its positions. So that means 1 plus 0, then 0.707 plus 0.707, like that position wise addition. This is what the sequence x of n we have got. For this sequence, apply the DFT and this is what x of k we are going to get. And now this is going to be the LHS part of the linearity property. Now we can observe the LHS part is equal to RHS part and that's what representation we have done over here and it is going to satisfy the condition of linearity property. Now let us go through the Scilab program for this one. So now in the program, so whatever the values we have discussed in the example, same values has been taken over here. So instead you can also provide an input directly of whatever the required value. So x1, whatever the value discussed, same value has been taken, x2, same value, and then a is equal to 1 and b is equal to 1, that has been considered. the length of the sequence n is equal to 4 is what is under consideration. Now verifying for the property. So term 1 we are calculating, that is with respect to LHS proof. So here a x1 plus b x2 we are considering. So a is equal to 1, b is equal to 1, and x1 is we are having the value over here, x2 value we are having over here. Now these values are added with respect to position and we are going to get this term 1. Then we are going to apply the DFT for that term 1. So we have got one result with respect to the LHS part. And then in the RHS part, individually we are going to apply the DFT for x1 and x2, and then we are going to add those results, and that is what is available over here. So FFT of A into x1, that is one term we are going to get, term 2. FFT of B into x2, another value we are going to get, that we are calling it as term 3. Now add these two values. That's what RHS part we are going to have. And now compare the LHS and the RHS part. If they are equal, then we have proved the linearity property. If they are different, then there is something wrong with the procedure. Right? Now let us go through the simulation of this one. Now here is the answer what we have got. So this what LHS result. So LHS in the sense, so we have first added the time domain values, then applied the DFT to that one. This is what the result. Second part, the RHS, first apply the DFT to individual time domain signals, then whatever the answer we have got, add those answers. That's what the RHS part we have got. And here we can have a comparison visually, and also in the program we are going to have a verification in the if statement stating LHS is equal to RHS, then write as linearity property is proved, and that is what we have got. If it is going to fail, then it is going to say DFT is not linear. In this case, it is a linearity property has got satisfied. Thanks for watching.